This video we will study the rectilinear kinematics for the erratic motion. Uh, Before we start with the erratic motion, we have a little bit review for the three main kinematic equation that we know that is V equal to ds by dt, A equal to dv by dt, and A ds equal to v dv. And these are the function of time for the case that if s is a function of time, so then it means that when we take the first derivative to this function, we get the velocity v. And also when we take the second derivative to this equation, we will get the acceleration a. Okay, so for the previous topic that we have learned, uh, it is a continuous motion. It means that the position, velocity, and acceleration can be described by a single function. But for the case of erratic motion, it means that the position, velocity, and acceleration cannot be described by a single continuous function along the entire path. So it's maybe when we have to solve this type of problem, we may change the the, the equation. We may show the equation, solve the equation in terms of the graph. That is that's something like this. For this case, this is the example of the train has the erratic motion. You see that the time from time equal to 0 to time equal to 30. It is defined, the position is defined by the first function that is s equal to 0.4 t squared. But for time from 30 seconds to 40 seconds, the position is defined by another function. As you will see that it is not continuous. Okay, it is not the same single function. It has two functions. That is the first one, and the blue is the second one. So according to this, if we show the, the the motion of the particle in terms of graph, it may be better to solve the problem. And we will use the relationship between position and time, velocity and time, and also acceleration and time to solve the problem. So let's take a look first. Relation, that is the position and time. This is the ST graph. When we plot the ST graph like this, okay, this the y-axis is S and the x-axis is time. Okay, for example, if for this graph, okay, we will see that for the position and time, if we take the first derivative, as we know from the kinematic equation, that you know that v equal to ds by dt. And for mathematics, we know that the first derivative of the function means the slope of the function. So it means that when we take the first derivative of the function, if we plot the graph, we can see that the slope at any point of the graph represent the velocity at each point of the motion at each point of time. Okay, so when time equal to 1, we take the first derivative at this point, we get the velocity at this point. Okay, and this means that if we have ST graph, we can construct VT graph by using this equation. That is, if the position of a particle can be plotted over the time like this, okay, the particle velocity as a function of VT graph can be obtained by determining the slope of the ST graph, and then we use the slope to plot the VT graph. Okay, so then we can, if we have ST, we can plot VT also. That is the first one. And next, if we know the information for velocity and time instead, okay, so then we can plot VT graph, okay, we can plot VT graph, and if we recall the kinematic equation, the second kinematic equation, that we know that A equal to dV by dt, okay, for A equal to dV by dt, it means that the slope at any point of the VT graph is mean the acceleration at that point, at that time. Okay, so then if we have the VT graph, we can construct the AT graph by using the slope. Okay, then the slope of VT graph equal to the acceleration. Okay, so then we can construct AT graph from VT graph like this. Okay, and if we know the information of acceleration and time instead, okay, so then we can plot the AT graph first. We can plot the AT graph, okay, and from the relationship of acceleration and velocity, we can rearrange this equation to be like this, become dV equal to ADT, right? And after that, we integrate both sides. So then from t equal to t0 to t, okay? And this is from v0 to v. So then on the left-hand side, we get v minus v0. And on the right-hand side, we have the integration from t0 to t. That is represent the area under the curve, under the AT curve. Okay, integrations of ADT is equal to the area under the AT curve, and it's represent v minus v0, that is the change in velocity delta v. So we can construct, if we know AT graph, we can construct a VT graph from AT graph by using this relationship, by determining the area of the AT graph. But we have to know that it is the change in velocity. It is not equal to velocity at that point. It is a change in velocity. So we have to know the initial velocity of the particle at each interval. So for example, like this, we determine the red area of the AT graph, and then we can change the area of the AT graph, the red area is delta V. So then if we know the initial velocity, we can determine for V1, okay? Because V1 is equal to V0 plus delta V, that is the area, okay? So then we can construct the VT graph from this way. In the same manner, if we have VT graph, okay, and we would like to construct ST graph, okay, so we use this relationship, that is ds by dt is equal to v. So then ds equal to v dt, and if we integrate both sides from t0 to t, okay, this is s0 to s. This means that if we know the initial position, we can construct the ST graph from VT graph by determining the area under the VT graph, and it's become the change in position delta S. And if we know the initial position, so then we can determine for S1, that is S0 plus delta S. Okay, That means that we can construct the S3 graph from VT graph by this way. Okay. So let's take a look for more complicated case. That is, we know the relationship of AS, acceleration and position in state. Okay, we have the relationship between acceleration and position, not acceleration and time. Okay, so then when we consider the relationship, the third kinematic equation that we know, ADS equal to VdV. Okay, ADS equal to VdV. So then if we integrate both sides, okay, and set up, integrate from V0 to V, and integrate from S0 to S, okay, so integrate ADS is the area under the AS graph. But for the integration of this term, if we consider this, when we integrate this term, we obtain V squared over 2 and form V0 to V. So then we obtain from V0 to V, we obtain this equation that is a half V1 V square minus V0. This is from V0 to V1 if we change the limit of equation to this, and S to be S1. Okay. So we have the left hand side, we have this term, and the right hand side is the area. Okay. So I sorry, I changed the notation a little bit. It should be S0 to S1. Okay. Okay, according to this, we will see that the area of the AS graph is not the change in velocity, okay, but it is the area is not the direct change in velocity, but it is equal to this term. See, it is equal to a half V1 square plus V0 square. Okay, so if we would like to plot Vs curve, if we know V, okay, we can, if we know V0, we can determine for V1, okay, according to the area, okay, according to the area. If we know the area, we know V0, we can determine V1 from this equation. Okay, so then after we have V1 for each point, for each position, we can plot Vs graph by this way. Okay, in the same manner with Vs graph, if we know Vs graph instead, okay, if we know Vs graph, we use the same relationship. We know that ADS equal to VdV. Okay, so from this equation, we rearrange this equation to be A equal to V dV by ds. This means that dV by ds is the slope of Vs graph. Okay, so it means that if we have Vs graph, the slope of the graph, okay, multiply with its velocity at this position, we will get the acceleration. Okay, so when we have Vs graph, if we would like to construct As graph, we just determine acceleration from this relationship, that is, we multiply the velocity at this time at any position to the slope of the Vs graph at the same position. You get the acceleration at that position. and then we can construct AS graph by this way. Okay. So next is we will talking to the example, some examples. In next video we will talking with the example that we will come back to next video.